Okay, so if you're given a table of data and you're asked to punch it into the calculator and come up with some regressions, a linear regression and an exponential regression. So let's review that real quick. In your calculator, you press home button and we are going to add, let's just clear everything out. Let's add a brand new document. So hit 1. You don't want to save any changes. And then let's add a list. Okay, now in your list, so let's get a header for column A, so we'll call it depth, and then in column B, pressure. Okay, now in cell number 1, we'll go 0, 10, 20, 30, 40, 50, 60. Then in B1, 14.7, 19.03, 23.36, etc. Okay, so once you've got your data entered into a spreadsheet in your calculator, then we're going to add another page. So you can go back to the home, and we want to add the pink one, the data and statistics. So hit enter. Okay, now so I got 1.2 and 1.1. So if I go control left, I can tab back and forth between my pages. So this second page, I've got these points plotted. Now click on your x-axis and it'll ask you which column do you want it to be. Do you want it to be the depth column or the pressure column? So let's put the depth column there. Then come over to your y-axis and let's put the pressure measurements there. Okay, and just the appearance of it looks like it's gonna fit a linear model really well. So now once you've got your x-axis and your y-axis all put together, everything's going to be in your menu. So click on your menu and you want number 4. We want to analyze. So just hit the number 4 and option 6. We're going to do a regression. Okay, now regressions first. Let's do a linear regression. So click on that and it will come up with a model based on the data that you've plotted. So this linear regression, I'm going to write it down, y equals 0.433 x plus 14.7. So now if we go back to our paper here, so there's your linear regression. So it was y equals 0.433 x plus 14.7, and based on this, this is my x and this is my y. So y is actually calculating the pressure. So the pressure depends on 0.433 for every x, which is foot. 0.433 every foot plus the 14.7. Okay, now an exponential regression. So I'm going to go menu and I'm going to do the same thing, analyze. I'm going to go into my regressions, and first I'm going to take that one away. I'm going to hide the linear regression I just did. So now I'm going to go menu, analyze, regression, and let's show an exponential regression. So an exponential is going to be, it's going to curve, it's going to change every single time. Linear is constant, so every depth change is going to be a constant rate of change. The exponential is going to speed up the deeper you go. Okay, so, and maybe let's just round that to 4 decimal places. Alright, so y equals 15.921516 times 1.0168. So if I round it just to 4 decimal places, my exponential regression is going to be this. The pressure is going to equal 15.9216 times 1.0168 raised to the foot. So we have used the calculator, we found both regressions, used both functions to predict the pressure at 120 feet deep. So now here's what we got to take. We got to take 120 feet, we've got to plug it into this model, the linear model, times it by 0.433, add 14.7, and that should be the pressure. So if we do that, I'm going to go 0.433 times 120 plus 14.7. So the linear model gives me a pressure of 66.66 pounds per square inch, whatever the pressure is. Okay, the exponential, I'm going to take that 120 and I plug it in there as an exponent. So 15.9216 times 1.0168 raised to the 120. Okay. And it is going to give me a pressure of 117.558 pounds per square inch. So they're quite different. 67, this is almost doubled. 66 and 2/3 pounds per square inch versus 117.558 pounds per square inch. Which regression seems appropriate? And it actually is the linear one. This one does have a constant change every time. So the linear one's going to be a better model because every time it is changing the exact same thing. It's changing like 4.3. So from 14.7 to 19.03, every time you go 10 feet deep, it's changing 4.3 pounds per square inch in pressure. So the linear one's going to be better. It fit better. There's a straight line. All those dots lined up straight. So we'll use the linear model. So it's going to be way closer to 66 than it is to 117. Okay, now your linear models versus your exponential. In 1990, the church congregation had 220 members. 2003, there were 441 members. Assuming that the number of the members in the congregation follows a linear model, we're going to find, so this one was a homework problem, and this was way good, but I want to show you something with the calculator. So these years kind of make it tricky. So if we create a table and we go year and number of members, so in 1990 there were 220 members, and then in 2003 there were 441 members. So I'm going to, just for mathematical purposes to make it easier, I'm going to say this is year 0. So at 1990, I'm going to call that year 0. Now 0 usually is the initial value. That's where it begins. I know it did not begin in 1990. They just gave me two random things. 1990 I got 220 members. 2003 I got 441. But I'm going to say, just to make the math easier, that 1990 is year 0. So 2003, the difference between 2003 and 1990, this would make that be year 13. So change of 13 years between those 2 points, and let's find the change in members. 441 take away 220. So the change here is 221 members. So if I had a change of 221 members over a 13-year period and it's linear, that means they're increasing at the same rate every year. So if we do 221 divided by 13, that is equal to 17 members per year. So every year I'm getting an increase of 17 members. So your linear model is y equals mx plus b. So y is going to be the number of members. The m is the increase, which is going up 17 per year, plus b, which is your initial. That's what you started out with. Now, here we go. Let's say that I started out with, let's call this the initial year, but it really is not. But let's use it to make our math easier. So 220. So I'm going to use this y equals 17x plus 220. Now I'm going to plug this function into my calculator. So in your calculator, I've got 2 pages open. I got page 1, page 2. I'm going to add a new page. So if I go to my home, I'm going to add a graph, hit enter, and your function, this is the y, so I got y equals 17 times x plus the 220, and if I hit enter, it's not going to appear on my screen because my screen only goes up to like 6, and I'm in the 200s. So, okay, so what I'm really interested in seeing is the table. So if I go, once I've got the function graphed, if I hit menu, and we want to look at the table, if we go number 7, if I split the screen with the table, and now, so your table, year 0 we had 220, then each year it's going to go up 17. So we can pick back here and kind of do what Haley did, or you can peek back and find right here. If you start subtracting 17, so we had 220, if you start going back 17 at a time, take away 17, how many years do you go back to find the original number of members? And there it is right there. So I cannot have a -1 person in my congregation. So this is going to be the original year right here. So the original year I had 16 people, and it was back 12 from when I started, when I set that 1990 equal to 0. So if I go back 12 years, I've got an original member of 16. So here we go. The year of the congregation, that's kind of what we just barely found right here. The year it was founded 12 years back. So if I take the 1990 and I go back 12 years, that is 1978, and there were 16 members present. So this is the real 0. But you can call anything 0. 0 can just be your reference point, as long as you know from that point you go forward, from that point you go backwards. So let's look right here. We can go the size of the congregation in 1998. If we're going to use this as our reference point, how many years am I going to plug in? So my function is going to equal y equals 17 times the number of years. And since I'm saying 1990 is 0, I'm going to go 8 years beyond that. And then I've got a plus to that, how many I had in 1990, which is 220. So 17 times 8 plus the 220. There's going to be 356 members in 1998. We just figured out when it was founded. We looked at the table and went back to when they had their very first positive number of members. Started off with 16 people. If the capacity of the church is 600, so they can hold no more than 600, when will it reach its limit? So 600 is that number right there. It's the population of the church. So I'm going to go 600 equals, and I'm going to go 17 each year, but I don't know the year, so that's X. But I'm gonna reference it from this 1990. So there were, whatever I need to do, I need to add 220 to that. So if I minus 220 minus 220, so 600 minus 220, that's going to be 380 equals 17x divided by 17 divided by 17. 380 divided by 17. Oops, 380 divided by 17. And it is approximately 22.35 years from 1990. So if I take 1990 and I add 22.35 years, that takes me to 2012.35. So the idea in this one is really, if you choose to set whatever year you want as your initial year, from that point is where you're going forward and backward. So we don't always need to call 0 the very, very, very beginning. In time, when you're working with all these dates, you can choose a date and call that your reference point, call it 0, and from there work forward. Okay, let's look at this one right here. James has $2,500 in his savings account, deposits $250 every 2 weeks. Lisa's got $500 in her account. She deposits $175 every week. Assume that no withdrawals are made and no interest is added to the account. So we're going to put these into a Google Sheet. So let's find the function for James. So James, his function, alright, he had $2,500 initially and he deposits $250 every week. So James's money, his total is equal to, now here was the trick, he's depositing $250 every 2 weeks and she's depositing weekly, so I've got to change them both to be weekly. So James is actually depositing $125 every week, plus I add to that is $2,500. And then Lisa, she starts off with $500, but she deposits $175. So Lisa, here we go. Her money is equal to $175 each week plus the $500 she started with. So these are my two functions that I need to put in to a Google Sheet. Okay, so here we go. Let's see, that's not the one. Okay, so your Google Sheet, we're going to do this. We'll call this week. We'll do one for James, one for Lisa. So let's start that week 0, 1, 2, 3, 4. So you grab a few, drag it down to whatever you want. Okay, now James's formula, so we're going to start off, we got to hit equals. And James's formula is going to be 125 times the week. So we're going to reference back to the week. So I'm going to click on this right here. And then after you do that, you add his initial 2,500 bucks. So there we go for James. At week 0, before we start, he should have 2,500. Let's drag that a few. And every week that goes by, it should just go up 125 bucks. So that looks like we're on. Okay, now Lisa, let's put equals. She's adding 175 times each week. So I'm going to have it reference back to the week. And then I'm going to add 500 to hers. And let's drag hers down. Okay, there we go. So I'm going to keep dragging them down. Maybe I'll go to 50. So if I go, okay, 51, that's good. So I'll drag her. Alright, so now we got a table for both of them. So James and Lisa, when are they going to have the same amount of money? So you can kind of, Lisa's, she's got some ground to make up. It looks like, where does she catch him? Okay, right here, look at week 40. So at week 40, they have the same. And then from that point on, she starts to overcome him. She grows at a faster rate than him. So he started out with more money, but she's depositing more money. So eventually she's going to catch him. And at week 40, she catches him. So we're going to insert a chart. To insert a chart, let's click right here. And it might already have it. Looks like my y-axis is money. This might be good. So let's see. So your x-axis, the x-axis, I want the x-axis to be column A, my time. Okay, there we go. Now your series, I have 3 series in here. I'm going to delete this series. I'm going to remove that. Okay, and we've got James and we've got Lisa. And instead of these bar graphs, let's go to the chart type. We don't want a column, we probably just want lines. Okay, there we go. That looks better. Okay, so now this looks pretty good. Lisa is in red, so she started out with 500 bucks, but her line is steeper because her rate of change is more than James. James started off at 2,500. At that point right there where they intersect, that is where they are equal, and it looks like that happened on week 40. So this chart's good enough. So the big thing is, I'm going to look for your formulas in B1. We should have a formula, some function that refers back to the week for James, one for Lisa. You can drag them as far down as you want, but I'm interested in your chart. Lisa's got to be steeper than James. They're both going to be linear. So now let's go back to, when are they going to have the same amount of money? At 40 weeks. So if you do it mathematically without even looking at the chart, we'll just set James equal to Lisa. So James was 125x plus 2,500, and we'll say he equals Lisa 175x plus 500. Now we'll just solve for x. So I'm going to minus 500 minus 500, and we're going to have 125x plus 2 grand equals 175x. Then I'm going to minus 125x minus 125x. And we got 2 grand equals 50. X divide by 50, divide by 50, and x is 40. And x is weeks, so at 40 weeks they're going to be equal. Okay, Lisa. Let's see if we can look at the chart for her. She needs to save 10 grand. When is she going to have 10 grand? So her function was 500 bucks plus 175x. So the math, I'm going to put 10 grand there and solve for 10 grand. But if we go look at the chart real quick, Lisa, does she ever hit? So I'd have to maybe drag hers down a little bit further. So I'm really close. So I need more time. Okay, 10 grand right here. So a little more than a year. 55 weeks she has 10 grand and 125. And at 54 weeks she has 9,950. So between 54 and 55 weeks is the answer. So somewhere between 54 and 55 weeks. Okay. So make sure you know how to type the function into a Google Sheet and kind of create some charts from that. Now the next ones are, so this is exponential growth. So the population of Utah was 2.233 million in 2000 and 2.763 million in 2010. Find the annual growth rate, that's kind of our K. And the function we're going to use, this population models, they're continuously changing. So we're going to use y equals a times e to the kt. T is time, k is our rate of growth, that's like your percent change. Between 2000 and 2010. Okay, so this is another one where if we use these years, 2000, 2010, I'm going to make it simpler and I'm going to just say 1 is times 0. So the year 2000, this is going to be my population. The year 2000, I had 2.233, and this is millions. Then 10 years down the road, 2010, I had 2.763. Okay, so I'm going to call this guy right here year 0. So this would be year 10 years later. Alright, so here we go. Let's see if we can use these 2 points to find our K. So that is my outcome. This is my initial value. That's what I started with. E is the number, 2.7-ish. That's your rate, and T is time. So I have everything but the rate, because my outcome, that's where I ended. I ended with this number right here. So I ended at 2.763. That's my start. I started with 2.233 times E. I have no idea what the K is, but I do know the T. That took 10 years. So I have everything I need. Now I just gotta undo all of this and solve for K. So first let's undo the multiplication. So let's divide this by 2.233. And these decimals are kind of bad, so it's going to get nasty. Do not round until the very, very, very end. 2.233. Alright, so let me punch that in. So we got 2.763 divided by 2.233. Okay, so you have some number. My next move, I'm going to take that 2.763 divided by 2.233, and that is equal to e to the 10k. Now, I gotta ditch the 10. Before I ditch the 10, I gotta undo the e, and the only way to undo this is a log. So let's morph this to its logarithmic value. So your log is gonna be in base e, so that's the base, and this is what I'm gonna take the log of. That number goes right there, and that is equal to 10k. So to morph an exponential layout to a logarithmic layout is not bad. That is always the base. Your exponent is always going to be what it equals, and this guy is what we're going to take the log of. So in your calculator, you punch in log e is the natural log, so either the natural log of that fraction, hit enter. Then all we got to do to undo the 10 is divide by 10, divide that mess by 10. So divide that mess by 10, and we found our k. Our k is equal to 0.02129710, blah blah blah. So it's a lengthy decimal. So that means if I move the decimal over twice, that's like 2% change a year. So our k, that seems right. It's increasing, kind of increasing at a rate of around 2% a year. So I'm going to use this for k. Now, I've got this k in my calculator, this long decimal. So I'm going to keep it in my calculator. Now, b, predict the population in 2030, assuming that it continues to grow at this rate of like 2% a year. Okay, so here's what I'm going to do. I said 2000 was year 0. I zeroed that out. So for 2030, I'm going to plug in 30 for my time. Now this time, I don't know the end result, but I do know I'm starting with 2.333, and I times that by e, and I know my k is this 0.02 blah 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 number, and I'm going to times that by 30. So this one I just plug everything into the calculator. There's no algebra, this is just straight up arithmetic. So 2.333, no, it's not 2.333, it's 2.233. So here we go. That's the detail thing. Gotta go slow and pay attention to detail. So 2.233 times e. I'm gonna go up and grab that k. So y equals 4.2302 blah blah blah, and that is million people, because we're in millions. So 2030, there's going to be approximately 4.2302 million. Okay, now C, when will the population reach 3.5 million? And that's where we're going to end. So this one we're going to have to do some algebra. So I want y to be 3.5. My initial, I'm still going to use that 2.233 times e. And the k, I'm still going to use that 0.002129 times t. So time is what I don't know. So I have no idea what the time is going to be. So let's solve for t. So let's divide by 2.233, divide that by 2.233, and we got this. We got 3.5 divided by 2.233 equals e to the 0.02129t. Now we're going to have to log it. So we're going to change this to a log. It is going to be log in base e of that number equals 0.02129t. So this is all calculator. So if I punch that in the calculator, we are going to get, divide that by, alright, so we get time is like 21.102 years. So 21 years down the road, so 2021, it'll double from, or no, it'll reach 3.5 million. Okay, and that looks like it makes sense. That fits, because in 2030 it was at 4.2 million, and so 2021 we are at 3.5 million. So that fits. So that looks good. Seems like it's a reasonable answer. Now find the doubling time. How long is it going to take to double? So we got really close to doubling in 2030. So if we start at 2.233 and in 2030 we're at 4.2, that's way close to doubling. So let me erase some stuff. So you can use like a quick calculation if you use the rule of 70. So the rule of 70 says you take 70 and divide it by your percent, which was 2.129%. So if I do 70 divided by that, I get like approximately 32.8 years. So it's going to take me close maybe to 33 years to double. So that's an approximation. If we want to figure it out, I'm going to take the doubling, so 2.233, and I'm going to times that by 2. So let's double that. 2.233 is going to be 4.466. Okay, so that's my outcome. That's my end result. So 4.466 equals my initial value, 2.233, times e to the 0.02129t. So let's solve it. So let's divide by 2.233, divide this by 2.233, and that should just be 2. So now we got this. We've got 2 equals e to the 0.02129t. And if we do log in base e of 2 of 0.02129t, this is actually 0.69, so this is the 70. But we just move the decimal over 2 times and change it to 70. So if we do log base e of 2, we get 0.69 blah 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 blah. Divide that by 0.02129, divide that by 0.02129. And if I use that I've got stored in my calculator, 0.02, the whole thing, and not round it, I get exactly time equals 32.54654 years. So that is dang close to the rule of 70. I mean, that's way close, plenty close enough. Alright, one more. So suppose the population of the town has a doubling time of 15 years. In 2011, the population was 32 grand. Okay, before you do anything, you have to find K. You got to find that the rate of growth, the percent change each year. And they didn't tell it to us. They told us that it doubles in 15 years, but we want to know how much it's changing each year. So here we go. So 2011, population is 32 grand. Okay, now, so let me define K. So if I take that 32 grand and I say that's my initial value, and I know it's gonna double, it will double to 64 grand, and I'm gonna times that by e to the k. I don't know what k is, but I do know that the time is gonna take 15. So if I divide that by 3200, divide that by 32 grand, geez man, 32 grand, 64 grand. Okay, I'm gonna have this. I've got 2 equals e to the 15k. So now I'm gonna take the log in base e of 2, and that is going to equal 15k. So divide that by 15, divide that answer by 15, and we just found k. So natural log of 2, divide that by 15, and our k, so we got to store this away. Our k is 0.4620981237. Alright, so I'm going to put that in the bank. So that's on my calculator. I've got it on my calculator. I can scroll up and grab it. So don't round until the very, very end. So now we can start. Now that you know what k is, so k, if I move the decimal over, that's like 4.6% a year. So if it doubles in 15 years, it's going to grow each year 4.620981% a year. Alright, so by what factor will the population grow in 90 years? So I'm going to take this initial value. I'm going to call 2011 the beginning. We'll call that time 0. So 32 grand is my initial. So 32 grand times e to the 0.046 blah 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 times 90 years. So they really want to know what factor are you going to times the population by in 90 years. They want this value right here. So if I go e and I go grab that k times 90, that is 64. So I am going to times 32 grand by 64, and that will give me my new population. So 64 is the factor that we times by. That's the answer to A. What population would you expect for this town to be in 2047? So I'm going to call 2011 0. So I'm going to minus 2011. How much time changed from 2011 to 47? That's 56 years later. So 56 is what I'm going to put in for t. So this one's all arithmetic. This one's not bad. So we're going to go, the population is going to equal 32,000 times e to the 0.0462 blah 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 blah. I'm going to use that whole number on my calculator times 56. So 32 grand times e, go grab your k, times 56, hit enter. You can anticipate the population is going to be it's going to grow to 425,593 and almost another person. When is the population going to reach 75 grand? That's what we're going to plug in for y. So we're going to go 75 grand equals the initial 32 grand times e to the 0.0462 times t. We don't know what that is. So let's undo the times. Let's divide by 32 grand. Divide this by 32 grand. And now you have 75 grand divided by 32 grand. And that's equal to e to the 0.0462 t. Okay, so we're going to go log in base e of that number equals 0.0462 t. So divide both those by 0.0462. And let's see what we get. Log we see of 75 grand divided by 32 grand divided by, so we get time is approximately 18.432 years. It's almost 18 and a half years it's going to take for them to grow to 75 grand. Okay, now to put this one into a Google Sheet, let me get it ready. Alright, so let's do this. So column A will be measuring by years. Column B will be population. So I'm just gonna start at year 0 now. Year 0 though, you gotta remember that's 2011. So maybe if I insert a column, so now check this out. So this will be the actual year, and I want 0 to correspond with 2011, 2012, 2013. So I started a pattern. I can kind of drag these down. So 26 years later from 2011 is going to be 2037. Okay, but these numbers for the math, I mean 1 is going to create a much better result than 2000. The numbers are smaller, they're going to work much better. Okay, so here's where you're going to type in your function. So the population is going to equal our initial value. Well, let's see, what was our initial value? 32,000 times e. So I will tell you what to write for e, so we all get the exact same answer. So I will say for e on the test, I'll tell you exactly how many digits, but e is close to 2.71828. Now I'm going to put this in parentheses. So e raised to the power, and I'm going to kind of put my exponent in parentheses because my exponent is two things. It's a k and a t. So for my k, and I'll have to specify what you use for k so we all get the same thing. So if I say use k to 4 digits, that's going to be 0.0462, and you're going to times that by the year, times that by t. So I want it to look back and times that by that right there. So close your parenthesis and hit enter. And in the beginning, we should, if we did it right, we should have a population of 32,000, which was 2011. Okay, now if I drag this formula down, there we go. Let's see, 20. Well, so one of the questions was like 2047. So if I drag this, I'm going to go another 10 years. I went a little far, but, and you have to go back, you have to establish a pattern. So you've got to grab at least 3 or 4 of them and then drag it down to continue the pattern and drop them all on the same line. But this one I don't, because this one is a formula, and each formula is referring back to this year column right to its left. So here we go. So in the year 2047, I can't remember what we got, but in the year 2047, if we got 168,837, and I don't even know if I saved it on there. I can't remember what we got, but hopefully it was something close to that. Okay, so then insert a chart. So you click here, and it might do it for you, the year, the actual year. Okay, that's way cool. So the actual year shows up, and then the population shows up, so it kind of intuitively knew to skip for the years. That's crazy. So look at your series. I've got my x-axis is the actual year, which is what I want. And we're just looking at population. Okay, that's cool. So then submit me your link and we're in business.